You have fallen into Event Horizon with John Michael Godier. Joining John today is Dr. Alexis L. Quintana. Dr. Quintana is an astrophysicist specializing in stellar astrophysics, galactic structure, star formation, and core collapse supernovae. He is affiliated with the Departamento de Física Aplicada at the Universidad de Alicante in Spain and the Astrophysics Group at Keele University in the UK. His research delves into the role of supernovae in enriching the interstellar medium with heavy elements which contribute to the formation of new stars and planets.
Dr. Alexis Quintana, welcome to the program.
Thank you for inviting me in your program.
Now, Doctor, you have been working with a very special class of star, a very scary class of star, O and B, these giant, massive, hot stars that have a strong tendency to live a short life and explode. What drew you to looking and cataloging OB type stars?
I think, it could be there are several motivations because these type of stars are very important in our Milky Way in general. So you mentioned that they have a short life, which means that they can be used, for instance, as tracers of star formation because they will remain, because they won't live long, so they evolve rapidly. So they can be used to study the stages of star formation. And also because a star in our Milky Way professionally form within the spiralams, these type of stars can also be used to trace the spiralam structure. And this is one of my main project because we need this type of tracers to really trace the position and motion of the galactic spiralams because contrary to other galaxies, we can't observe them directly. We need to, since we are looking from the inside. And also, you mentioned the supernovae, and it's important to look at the position because for future generations of gravitational wave detectors, they will be sensitive to the emission produced by these supernovae. So it's good to see where they are located. And what motivated me as well is that this type of stars can be better observed nowadays with the availability of bigger surveys and big telescopes. I'm mainly using data from my research. I don't know if you would like that I describe in a bit more details, but let's say that there have been new data releases within the past few years with more coming within the next few years that allows us to map the 3D positions of stars in the Milky Way with greater accuracy than ever before, which is a great motivation for building new catalogs of stars, including these OB stars for all the reasons I've mentioned.
Now, in regards to star formation and tracking star formation, I take it the reason that you would study OB stars is that they live such a short amount of time, a few million years.
Yes.
And that means they live and die close to where they formed, right?
Yes.
So that's the key to it, and that you study those. But the problem is that stars move, and the sun moves. Each star has proper motion, and they're also orbiting the galactic center, which means that stars go through close encounters. And we have evidence that this star system was once very close to a supernova because it's populated with heavy elements. And there's certainly almost a certainty here that the star system has seen several close supernovas just over the last billion years. And you came up with a number on that. What was it, and how often does the solar system see a relatively close by supernova enough to be damaging?
A number I found in the paper is about 2.5 per billion years, which is about one every few 100 million years, which I guess it will be a follow-up question. But this coincides with the rates of several mass extinction event on Earth. So let's say that this threat is occurs over the scales of several millions of years. This is one of the main conclusions of my study. So this is consistent with two main extinction events, which had not as known causes as the one who killed the dinosaur. That we know it's due to an asteroid. There were more unknowns about the cause, and the the research I found is consistent with a nearby supernova being the driver of these mass extinction events.
One of the things that piqued my interest about your paper is that it also is corroborated by something else. We're finding iron nuclei, isotopes of iron that appear to have originated in a supernova event. And we see them in Antarctica and, ice cores. We see them on the moon. The detections of these iron nuclei that are pointing strongly to frequent supernovas, right? That does corroborate what your work, right?
This is indeed something I've discussed in the paper. So the amount of this iron isotope that have been found, like in notably the Apollo lunar samples or in the Antarctic ice, which, as you said, corroborates like the numbers are found from the sample of OB stars.
Now, in the extinction events,
yeah,
what is the mechanism that a supernova has that can destroy some measure of life on Earth? Is it basically just cooking off the ozone layer and causing ultraviolet from the sun to get in? What exactly happens when you have a supernova extinction?
Okay, so if we start from the explosion, so the supernova phenomenon is very high energy. So if you've mentioned ultraviolet radiation, so when this ultraviolet radiation will reach us, it will interact with the particles of the atmosphere. So these particles, carried by the supernovae, they are called the cosmic rays. So cosmic rays can have a lot of sources, but supernova are one of them. And through this interaction with this of the cosmic rays with the particles of the atmosphere, it will cause the depletion of the ozone layers, which means that the Earth will cool down because the ozone layers helps to trap the heat received from the sun within our planet. And this causes mass glaciation events, and many species can't survive it. Hence the name of mass extinction event.
Yeah, especially oceanic life, where most of it lives just in the very, very upper layer, just underneath the surface of the water, and that opens it up for ultraviolet extinction. Now, what is the distance factor here? In other words, for supernova to cause an extinction event on Earth, what distance does it have to be within in order to damage the planet?
So the distance I quoted in the paper is 20 parsec, which corresponds to about 65 light years. There have been debates on the past. For instance, some people said that the kill radius was twice smaller, would have been more 30 light years. But more recent studies have found it's more likely to be 65 light years. And basically, a more distant supernova could still have an influence on life on Earth, but 65 light years is really the distance at which such an event will be devastating for life on Earth.
Now, with these type OB stars, what would that even look like? In other words, if you're seeing a massive star like that at a distance of 65 light years, that would that outshine the moon? If you were just looking at it, a supernova aside, just the star at that distance, that big and that luminous, had to have been spectacular, wouldn't you think?
Yeah, this is something we could probably observe during the day. And if you look at the records of historical supernovae, I don't think they were outshining the moon because they were much more distant. But still, they were documented. I think I can't remember the name, but there was a supernova explosion that was observed in ancient China 2,000 years ago, and it was really prominent, so really luminous, and it was everyone could see it in the night sky.
Yeah, that was the M1, the Crab Nebula formation, I think, as I recall, the Chinese astronomers had recorded. Now, what about remnants? In other words, can we look around at supernova remnants relatively nearby and try and track down what supernovae might have caused these extinctions, or is that stuff just too far away at this point because it was hundreds of millions of years ago?
Actually, it's not an issue of distance. It's more an issue that the remnants won't last as long. So basically, I think there are a few tens of supernova remnants that are known in the galaxy that are notably been studied in the radio and high energy domain. But let's say life expectancy, if we could say that for supernova remnants, is only a few thousand years or a few tens of thousand years, after which they will, I don't know if dissolve is the right term, but through interaction with the interstellar medium, the particle radiation will just merge with the interstellar medium. I don't know if it's the correct word, but I hope that can give you the right image. And the scale that we're looking for the mass extinction events were hundreds of millions ago. So it's not something we could observe in the supernova remnants, unfortunately.
Now, the two mass extinction events that you were able to correlate this to, which ones were those? What are the time frames roughly that these extinctions occurred, and what happened? I mean, how bad were the extinctions due to supernova? So
the two events I was referring to in the paper are the late Devonian and Ordovician events, which occurred about 372 and 445 million years ago. So It's separated by about 70 million years. How about that? So I can't remember the exact number, but I think it killed about 70 or even 80% of all animals, well, all the food and maybe like also the plants. I think the numbers I've seen is for the animals, but it was like the majority of them, like a big majority, 70 or 80%.
And these were basically what you would expect from ultraviolet exposure. In other words, they were great marine extinctions, and that the actual death toll was largely in the oceans, which I guess is what you would expect from a supernova extinction.
Yes, and I think at this time, like most of the animal life were in the ocean. I'm not exactly sure, but I because not a geologist, but I think that's true, right?
Yeah, I believe so. I think everything was mostly marine back then, although that's slightly changing a little bit as the paleontologists do their work. They're starting to understand that maybe some stuff could selectively go and live in an air environment for a little while and things like that. But that happens with the oceans today. I mean, you will see occasionally an octopus leave the ocean and go onto a beach to escape a shark or something like that and then go back in. So it wouldn't be surprising. But still, that would actually make it an even more dangerous environment because you would be in the raw ultraviolet. So anything that was climbing on land probably didn't survive this. What is the nearest O or B type star to us now? In other words, when is the next event?
So, well, we don't have to worry about that in the near future because Betelgeuse is one of the most famous one. It's like a massive star in its red supergiant phase, so it's clearly evolved for a massive star, but it's located several hundreds of light years away. So if Betelgeuse explodes in the near future, which is still again speculated, it won't affect, could affect Earth, but not to a mass extinction level. And I think another one is Antares, and once again, it's like several hundreds of light years distance. So we don't have to worry about that in the near future. So in the paper, I wanted to emphasize that this is something that occurred in the past and it could happen again, but within tens or hundreds of millions of years in the future. So it's not something that is an immediate danger within our lifetimes.
As a galaxy ages, does the threat level drop? Meaning, as a galaxy gets older and older, I would think that there would be less and less OB stars, right?
I think that's a great question, and it's more something that we could compare with other galaxies, because as we look at the population of OB stars, because of course they don't live long, we look at the conditions of star formation, like the present condition of star formation, or let's say within the last tens of million years. So if we look at the late B-type stars, it's they can live hundreds of millions of years, but the stars that explode as supernovae, they typically, early B, and O-type stars, they typically live a few minutes to a few tens of million years. So would be hard to predict, but I think it's just that I'm an astronomer looking at the local Milky Way, but I know other astronomers are looking at other galaxies and looking at star formation history. So we're looking in the past, but I think from the studies I know, it's true that the star formation will decrease in the future, but it goes also for all type of stars. So life would be less threatened by these OB stars, but if fewer stars form in general, it means that there will also be fewer planets where life could emerge, because there would be fewer stars and around which they will orbit, if that makes sense.
Yeah, aging galaxies, reddening galaxies, basically. As they age, the powerful stars go away. But this is an off-the-wall question, but it's just something I'm curious about. As someone that studies OB stars, do these give us a kind of an insight on the still fabled type 3 or population 3 stars of the early universe? Now, granted, I understand that there's going to be a lot higher metallicity and all that stuff in these stars, but do these type OB stars give us any clues about the earliest stars in the universe?
I don't know if I'm the best person to answer that question, because I'm not specialized in the study of other galaxies. What I would say is that the newer generation of stars tend to be more metallic, and that's because they've been formed within environment in the stellar minimum that have been enriched by the explosions of these massive stars. So I think the earlier universe, the metallicity level within the environment, within the stars, was much lower than for stars of our sun's generation. But the conditions in general were very different. So I think like more massive stars could form. Like I think the limit today, well, according to stellar evolution models, is about 100, 120 solar masses. There are few stars, I think, observed in the imaginary clouds that can reach like 300 solar masses, but it's really the exception. But these models, if I'm not mistaken, show that there could have been more massive stars than that in the early universe. I don't know if maybe I have deviated a bit, but I hope you see where I'm going to.
Yes. Now, we're somewhat lucky in that we're in a quiet part of the Milky Way. We're just on the edge of a spiral arm, just out, not that close to other stars, but there are very dense regions in the galaxy, globular clusters, and of course the galactic center, where you're going to have a lot more supernovae packed in much closer. Do you think that's a showstopper for life? Do you think that just the supernova rate alone says, no, not likely anything could ever arise in a dense environment like that?
I think that's a very interesting question. So I see where I could start, but I remember a study that was showing like what would be the habitable zone of the galaxy. And I think that's a really elegant way of showing this because it connects to how we have been studying exoplanets and looking at the habitable zone of exoplanets that depends on notably the type of stars. So red stars will have an habitable zone that is much closer than from them than stars like our sun, for instance. So basically, the study was showing for the galaxy, and actually, the study was quite optimistic because it was showing that the habitable zone of galaxy could extend towards the outer edges of the galaxy, and of course, where our sun is, we are about halfway through, and the most hostile zone to life would be the galactic center. For the reasons you've mentioned, it's very dense, so the supernovae would pose a much greater threat than they do in our environment. So yeah, in a way we are lucky, but it also could be like some kind of confirmation bias. We know that we exist, so that we know that the conditions to form life within our environment are not as threatening as in other regions, such as the galactic center.
Now that's actually an excellent point that you can have biases when thinking about these things when you only have a sampling of one. Now, with the case of nearby supernovae, these seem, if indeed they are responsible for mass extinctions, which I think is a reasonable idea because that'll do it. But mass extinctions are known for basically restarting the evolutionary process. In other words, it just puts it on a different footing. Every time there's a mass extinction, something else comes out, and we're evidence of this because the rise of the mammals coincides with the asteroid that killed the dinosaurs. It just opened up new niches and closed old ones. Does that mean that for an evolutionary process to get to complexity like us, is it possible that it requires supernovae extinctions to keep everything driving along?
Well, that's a great question. I don't know if as an astronomer I could talk about how the development of intelligent life and what would have happened if supernovae weren't there to engender mass extinction. For instance, an idea that maybe is more like science fiction than or than really science, because I'm not a specialist, is like, for instance, if there weren't any asteroids to kill the dinosaur, what would have happened? Maybe the mammals wouldn't have evolved and we wouldn't have been there, but maybe like dinosaur would have remained, and maybe some dinosaur would have become like us, and there would be another intelligent people on Earth than us. But I mean, that's all speculative. So when I was referring to supernovae as destructors and creators of life, I think more referring to life in general on Earth. So basically, to continue on the previous questions, we talk of supernova as a destructor because if we are too close from them, this can engender a mass extinction event, so as we were discussing. But also, as we were talking about metallicity, so when massive stars explode as supernova, they will bring the heavier elements that will be used to form new stellar systems and new planetary systems, and include the elements that have been used to help life to develop on Earth. So that's a really interesting question, but it's for my knowledge, it's very speculative.
It's an interesting point that you made, that we are made of the materials of a supernova. The atoms incorporated in our biology, all the way up to things like uranium, which we don't really use that, but still all supernova material past a certain level. And That's interesting because you need supernovae to even have the stuff of life ultimately, right?
Yes, well, life as we know it, but again, it's a bit speculative because there have been questions about our life is carbon-based life, and there have been theories about silicon-based life, but all these elements are heavier, that the base elements that were there at the beginning of the universe, the hydrogen, helium, lithium. So even if we can imagine that other type of life as the life as we know it emerge, you still need the supernova explosion to produce the
Yeah, and I mean, remember, the universe started with just hydrogen and helium, a lot of it, and a little bit of maybe beryllium and a little bit of lithium. But fundamentally, it all started with hydrogen and helium, and you are not going to get life from that. You're not going to get much of anything from helium, not much of a reaction at all. So therefore, for a universe to become habitable, you must have these supernovae, and that's just the way it goes. Even to have a planet, even to form an exoplanet, you're going to need early supernovae to populate the universe with materials for it. I find that fascinating because it shows how the universe evolves and then it changes over time. Now, when you were doing the survey of the OB stars, what is the sampling? What was the size of your survey, and what instrumentation were you using to do it?
So I was mentioning Gaia at the beginning. It was really the core, the satellite that are at the basis of this research. I've used also other telescopes, but Gaia was especially important because, as I've mentioned in the beginning, it is the most precise 3D mappers that we know because it has measured the astrometry, so the parallax and proper motions, parallax that we convert into distances of about 1.5 billion sources. And it's really unprecedented in the history of astronomy because measuring the distances of stars, it's been very difficult in history. And even Gaia's predecessor, Hipparchus, was mostly limited to the solar neighborhood and to the brighter stars. Gaia really pushed the boundaries, and I think many astronomers are grateful for it, and I'm grateful for it because it enables the production of new catalogs. And this business in Gaia, combined with the photometry from Gaia as well, and the photometry from other surveys in the optical and infrared, allowed me to estimate the physical parameters of stars. And with the temperatures and luminosity, I could build a sample of OB stars in the solar neighborhood. So here it's a sample of about 25,000 ONB type stars within 1 kiloparsec, which more or less corresponds to 3,260 light years. So I don't know if you have any follow-up questions about this.
Well, frequency. When can we expect one of these OB stars in your catalog? Any of them. It doesn't have to be close to Earth. It can be anywhere in the Milky Way. When will the next supernova of one happen? Is it probably going to be Betelgeuse, maybe?
Well, Betelgeuse is one of the most famous ones, so that's why we having our eyes kept on it. But I've also I've quoted in the paper the frequency of supernovae. But I recorded 3 rates. So the rates near the Earth that could be damaging us, life-threatening even. So the rate at 1 kiloparsec, so the volume of the survey, and I've also quoted the rate over the entire Milky Way, which was extrapolated for the rate I found within 1 kiloparsec. And this rate I found is about half a supernovae per century. And it's actually a revised version of the previous estimations because estimations were of about 1 or 2 per century on the Milky Way. But it really depends in a way because some of these estimations were based on the rate of historical supernova explosions. And if you look at the 2 last explosions in the galaxy that were observed by Tycho and Kepler, they are only separated by 30 years. I think it's the 1572 and 1603, if I remember correctly the date, so separated by about 300 years. But then it has been 4 centuries without any supernova explosions in the Milky Way. And the last supernova that was observed in the naked eye is 1987A, which was in the Magellanic Clouds. couldn't see it, unfortunately. I wasn't born yet. But it shows that we have yet to see the next supernovae and in our galaxy, and Betelgeuse would be a nice candidate. But I think even Betelgeuse, they say they could explode within the next 10,000 million years. So it's quite a wide range. It could be way beyond our lifetime. But there could be another that we don't know about it, and we'll be surprised when we see it, because even with this revised version, it's half per century. So it's within a human lifetime that we could see the next supernova in our galaxy. And I mean, for me, it would make a great spectacle.
Yeah, supernova 1987A was maddening for me because I am old enough to remember it. I was in my early teens and getting into amateur astronomy when it exploded, and I couldn't see it because I was in the northern hemisphere. So I missed my supernova, unfortunately, unless something unexpected happens. But yeah, I do well remember that. But it's interesting because that allowed astronomers to track the evolution of what happened after the supernova when you look at the remnant. And it's been endlessly fascinating. Now, what's next in your research? Are you going to continue along these lines and do more with OB stars? And will the LSST, the Vera Rubin Observatory, help in that work?
Yeah, I've heard about the LSST, but I'm gonna use other instruments. So I'm still, continuing with Gaia, especially because the next Gaia data release will be end of next year, so late 2026, which will even further improve the accuracy of the parallaxes and pop motion from Gaia, which will allow us to build more precise catalogs. So one of the next follow-ups is to extend the sensors, because I did it up to 1 kiloparsec. So the idea would be to do an all-sky sensors. And the next step is to double the distance, so within 2 kiloparsec, which would make within the nearest 6,500 light years. And I was also talking about mapping OB stars. And one of my follow-up is also to look at the groups within which these OB stars are. So I probably know about star clusters, which are very compact, and OB stars are typically found within groups that are less compact and that are less dense in general, that we call OB associations. And they are important because basically they represent an intermediate stage between the star forming regions and the galactic free population. So it helps us to look at the model of star formation, because you have these groups that are discernible thanks to the OB, the brightest members, that will expand and dissolve after a few tens of million years. So it's important to map them, and with Gaia we can have constrained quite accurate distances for this association, especially the nearest ones, and we can revise the previous catalogs. And if we look at these associations, we can also learn many things. So to come back to the subject of supernovae, that's a study I quoted in my the study I quoted in my paper. It's basically we also there was a previous study that looked at how the local bubble around the sun was formed. I don't know if you've heard about it.
No, explain that.
Okay, so the local bubble is basically the environment within which our sun is embedded. So basically our sun is located in a cavity of lower density of gas than further beyond in the galaxy. And the reason why has been explored thanks to Hipparcos data about 20 years ago, and much more recently with Gaia, which confirmed the findings of Hipparcos. So you have the nearest association, which is called Scorpius Centaurus, which is about 150 parsec away, which is about 500 light years. And the study has found that if you trace back the motion of these members of the association in the past, they coincided with the position of the sun a few million years ago. And the most massive members exploded as supernovae, which blew away the gas in which the sun was, environment of the sun was embedded, and created this cavity as we know it today. So basically, if you have an accurate 3D mapper and you map this association in which the stars are contained, you can also tell about the star formation history of our local Milky Way and even further beyond. So I was mentioning the spirals. So the idea is to look in more general line is to look at star formation in the local Milky Way for me, using these OB stars and associations as tracers, and also looking at the structure of the spirals as I go beyond in the galaxy. And for that, the Gaia data will help, but also the future spectroscopic surveys that will, on the one help to constrain further or validate the physical parameters that are derived using Gaia and other photometric surveys. And on the other hand, they will also contain the radial velocities, because if you have the proper motions of Gaia, you look at the motion of the stars in 2D, and with the radial velocity, you look how if the stars are approaching or like getting away from us. So basically you have the 3D motions. And if you combine the 3D position with the 3D motion, you can really look at the past motions of these groups of stars within several tens of million years. So you're really learning about the star formation history and also about how the Milky Way spirals could have formed, which is another story. So there are plenty of things that can be done, and I'm really excited to work on that in the near future.
Oh, thank you for joining us today, Doctor, and I wish you great luck in further research. And it'll be interesting to see what the paleontologists come up with if they can find some indication that the heart of at least 2 mass extinctions were supernovae in the Milky Way.
Thank you.